you for joining us again with another live stream. And this time we are with Phil Seamark, who is in Power BI CAT team, and also who is the guy behind like a lot of DAX sessions, DAX books, and also articles. His blog DAX.tips is a wonderful resource for learning a lot about DAX measures, how they work, and things like that. Hey, Phil, how are you doing?
Oh, very good. Thank you, Reza, and thanks for inviting me on here.
My pleasure. Where are you based?
In Wellington, in New Zealand. So 7:30 in the morning. Quite a civil time for me. Quite enjoying this.
Yeah.
So yeah, and, Wellington, New Zealand.
Yeah. So like pre-COVID-19, I believe you've been airborne. So after COVID-19, based in home, right?
That's right. Yep. Really enjoying the extra time here in New Zealand, one of the most beautiful countries in the world. So
right.
Yeah.
Wonderful country. It doesn't happen much that I'm presenting with a person from the same country. So that's wonderful to have you here. Can you introduce yourself a little bit so our audience, just in case they don't know you, they get familiar?
Sure. So as Reza said, my name's Phil Seamark. I work on the Power BI Customer Advisory team that a lot of people call the CAT team. As part of my role there, I get to work with some large enterprise customers from all around the world and get to see all sorts of interesting challenges and problems that arise. People trying to do some clever things in Power BI, and part of my role is to help them solve interesting challenges. And actually what we're going to be talking about today is something that does pop up reasonably often. So that's why I thought I would put a basic session together and just walk through the session, but we'll leave it to that. So
that's great.
As Reza said, I tend to specialize in DAX and data modeling. It's a bit of a hobby. I quite enjoy it. Not many people do, but it's good fun. So, and hopefully the session today will be interesting and useful to you. So,
great. Thank you. Thanks for the intro. So everyone, you are hearing from the person with a lot of experience in this. He is dealing with a lot of clients with like bad data models, slow performance models, and he's helping them with solving all of these. Like if you have any questions, like Phil's contact details is under his video feed right there, LinkedIn, Twitter, and his blog. I highly recommend his 2 books as well. Do you have a third one in progress, Phil, or not?
Not this year, I'm afraid. No. I think what I need to do is go back to the first one and just do an update to it, just revise it, put in all the good learnings that I've picked up since I started at Microsoft. And absolutely, if you do want to reach out to me, please feel free. I can't guarantee that I'll respond in minutes, but I certainly enjoy relaxing the evening by working through a tricky problem that's come to me through the community, or on the weekend, when I'm just relaxing. So I'm not a big TV watcher or crossword puzzle person. I like to solve DAX challenges.
That's wonderful. Phil, before being a part of Power BI team, when he was a Power BI MVP, he was doing a lot of like community work, answering community.powerbi.com questions, and he was quite high rank on that as well. So yeah, feel free to reach out to him if you have any questions. Hopefully he'll find time sometimes to dig more into that and go through your questions. Okay, Phil, anything before we start? Anything else before we start?
No, that's all I can think of. So, and absolutely feel free to fire questions at us during the session.
Sure. And I see Adam also joined us. Wow.
Adam, hey, Adam,
nice
how are you?
Here. Yeah.
I hope you're not been blown away in that awful double hurricane over there in Houston. Keep safe, brother.
Yep, stay safe. Okay, great. So without further ado, I'll hand it over to you. Just one thing about questions. If you have any questions, feel free to write it in the chat window in the YouTube page. I'll be watching there, and I'll interrupt Phil in the middle of his presentation if the question is related to the topic. Otherwise, I'll just answer it over there. And that's it. Hand it to you, Phil. Feel free to...
Okay, cool. I'll share my screen.
Presentation mode.
Hopefully you can see something called my opening slide on my presentation.
Yep. DistinctCount for Power BI. Yep, I can see that.
Okay, so we've already done the introduction. So I'm Phil Seamark on the Power BI CAT team. And as I mentioned, I do get the opportunity to work on some really interesting large models. And some of them aren't very well put together, but some of them are actually extremely well put together. But we're still looking to try and eke out interesting performance gains by spending time on them. But one thing that's reasonably common that pops up is a lot of the times people say, hey, this particular report page is slow, and can you have a look at it? And when I do, I find that the reason why it's slow is because of this distinct count calculation that's somewhere in the page. And it's quite common for the slowest page on your Power BI report to be because you're doing a distinct count calculation. And for a lot of people, this is a bit of a mystery. It's like, why? Count sounds fast. Distinct is just grouping. So what I thought I would do today is just walk through a little bit of the reason why distinct count is one of the harder calculations for any BI tool, not just Power BI, to compute. I'm going to show you some, let's just jump to my agenda. We're going to look at some different options on how you can do distinct count in Power BI, because there's more than one way to write it. And the different ways that you can write distinct count have different pros and cons. And I'll have a little bit of a demo that shows some extreme examples of why that is, and hopefully that might make sense. And then after that, what we'll do is we'll have a little bit of look at some more extreme alternatives, like how you can use not a precise distinct count, but an approximate distinct count to possibly arrive at a number which is good enough for your report page. And then finally, we'll just recap everything we had a look at. But first of all, what I thought we might start with is a bit of an explanation as to why distinct count is that much slower than other typical calculations. And I thought what we could do is just imagine we had a data set that was based on playing cards. So if you took 5 packs of playing cards and shuffled them up thoroughly, and then just randomly picked out a handful of cards, say 20, 50, or 100, and you wanted to perform a calculation on the numbers. Now, I'm only going to use 5 playing cards in my experiment because that's all I could figure out how to animate using PowerPoint. But just imagine that this could be 20 or 100 or 200 random cards. And what we wanted to do was perform a sum. So in the cards that I'm showing you in my slide, we have a 3 and a 5 and a 7, etc. So what we're trying to do is arrive at, if we were to sum these numbers, what would be our end result? If we were to perform a max over these numbers, etc., an average, and we're going to look at distinct count. So we've got 5 cards here, and we're just going to walk through what each calculation does. So we're going to start with a sum calculation. So I've parked my 5 cards up in the corner. We don't know what they are yet. And the first card that we're going to look at is the number 5. And we'll see over here, I'm not sure if you can see my cursor, hopefully you can. What we've done is we've allocated a piece of a portion of memory just to store a single value. And what we've done at step 1 is put the value of 5 into that piece of memory. And then what we can do, after we've looked at the first piece of data, or the first card, we can throw it away and grab the next card. We can go back to our piece of memory that we previously had the value of 5 in it, and we can increment it. We can update it to a new value or overwrite it. So we're not using any more memory to do this. Now let's look at the third card, because we can discard the second card now. And it's the same pattern. We can look at the value on the card, i.e. the next piece of data. We can increment where we're storing the value now to 17, overwriting the previous value of 8. And now we can discard the card. And we can repeat this through to the end. And we arrive at a value of 29. We've used very little memory to complete this calculation. And a couple of notes about this are, we only needed to do one pass through the cards. We didn't need to sort the cards at all. We only needed to increment a single value. And this is really important when it comes to memory. There's no need to keep track of the cards read. And this is a really neat thing as well, is that we can use this work, the single pass that we just ran through, to create subtotals and totals, because when you perform a sum calculation over perhaps what is the sum of items sold on during the days of a week, we can perform this single pass through. But then when it comes to producing a value for the total for the week, or the total for the month, we don't need to go back to the cards. We don't need to do a second pass. We can just simply look at the results and sum them up. It's much easier. It doesn't require anywhere near as much memory. So the next thing, the next calculation we're going to have a look at is the max calculation. So we're going to use the same cards and we're going to do the same exercise. So we look at the first card, we look at the value, and we store it into memory. Then we throw the card away. We look at the next card, we check to see, am I higher or lower or not? I'm not higher, so we can just simply discard the card, no action required. The third card, we check, am I higher than what we had stored? Yes, I am. So let's overwrite. We have a new value, and we can discard the card. Then we look at the fourth card. It's not higher, so we just throw it away. We look at the last card. It's not higher. We throw it away. So the characteristics are very, very similar to sum. We only need to perform one pass through the data. There's no need to sort. They could be. We could look at these values in any order. We only need to increment a single value in memory, so we're not using much memory to actually work through this process. We don't need to keep track of cards, and again, we can derive subtotals and totals, which is really useful. Now, the average calculation is slightly different to the sum and the max calculation. What we need to do here is, like sum, allocate a piece of memory to keep track of the incrementing value, but we're also going to have a second value that we're going to increment to keep count of the number of cards. So let's now click on the next card, which is a 3. Now, the first value here on the left, we're going to increment by 3, and that's now 8. The value on the right is our card counter. So let's just flick through these again. 17 divided by 3 is our average. 24 divided by 4 is our average. And finally, 29 divided by 5 is our average. So again, let's have a look at the characteristics of how to perform an average-based calculation. We still only need to perform one pass through the cards. So that's great. There's no need to sort. But what's not so good is we need to keep track of 2 values, but it's not a huge tax on memory. We need to increment 2 values and keep track of the number of cards read, and we can derive. Now, how does DistinctCount calculation? Now we've got a handle on what those more common types of calculation do under the covers. Let's have a look at the DistinctCount. So let's have a look at the first card, number 5. We're not going to keep tallies of any number. We're not going to keep track of any numbers. What we have to do is park this value somewhere. We need to put it into memory to know that, okay, we have a 5 of clubs. And when we have a look at the second card, what we need to do is go and check, have we seen this card before? Yes or no? We haven't seen the card before, so we need to actually now allocate some memory to put this card into memory. And we can see the memory required has increased there, and we're storing the values over here. Let's draw the third card out. It's a 9 of clubs. The first step, we need to now go and check all of the values that we've previously seen to check, have we seen this card before? And in this case, no, we haven't. So we need to go and store it into memory. And the pattern, as you can see, is the same. Have we seen the 7 of hearts before? No, we haven't. Okay, so we need to actually park this into memory. So not only are we passing through the cards in the data set, we're having to do a subset of pass, which gets incrementally longer and longer to check to see whether we've encountered this card before. And we're going to park this into memory. And as you can imagine, when you've got a high number of unique values in your data set, this is going to start causing some real problems for your memory. Lastly, in my data set, let's bring down the 5 of clubs. We'll check all the other values. We only need to check one. If we look at the first card, happens to be one we have seen before, so we can discard that. So the characteristics are: one pass through the data stored in the data set. There isn't any need to sort for this approach. We need to keep track of every single group in memory. of previous cards that you've seen. Now, imagine you're doing something like, I want the distinct count of users that have used Facebook this year. You know, it would be a huge number. That would wouldn't be taking seconds to complete using this approach. Each card needs to check if it's new. And another really important thing that distinguishes distinct count from the other types of calculations that we've had a look at so far is that you can't derive subtotals and grand totals like you can so easily with the sum, for example. And I'll just explain what that means. So imagine that you have a shop and you want to keep track of the distinct number of customers that visit your shop. And on Monday, we have bin, nat, and bin come into your store. So the number of distinct customers here are actually 2 because bin came in twice. On Tuesday, we saw Adi, bin again, Ash, and Adi. So we have 3 distinct customers visit the store on Tuesday. On Wednesday, there were just 2. Thursday, we had Vic, Nat, Adi, and Bin, so we had 4 distinct customers. And lastly, for the last day of the week before the weekend, hooray, is we had 2 distinct customers, Ash, Vic, and Vic. So if you can imagine, you were running a pivot table, each one of these values would have performed the previous step in a unique way. Going and allocating memory, checking to see whether they've seen the card before to arrive at these numbers, but we can't use any of these values in this column to arrive at a total like we could have done with sum, max, min, average, etc. So what we need to do, if we wanted to show a distinct count of the customers that visited our store during a week, we have to go back and start again and perform that exercise that I just showed you with the playing cards, go back to the database, clean, and say, give me all the rows in the database that are relevant for the entire week, and start bringing the values in. So we would look at bin, put them in memory. Look at nat, put nat in memory. Then look at bin again, go, aha, we've already got bin in memory. I can discard bin here, and then slowly go through all however many people are actually represented here, and the total amount is in fact 5. But there's no way we can take advantage of this. So not only are we doing extra work for these individual lines, we're having to start again and do the overall work over here. So hopefully that gives you a sense of why distinct count ends up being quite slow, just simply because of the amount of work it needs to do under the covers just to arrive at a number. Now, if you're talking small numbers and small data sets, you don't notice this. But when you start playing on much larger data sets, and particularly if you're trying to perform a distinct count that's going to end up being a very high number, then it's going to force not only a lot of time, but a lot of CPU and a lot of memory usage. And while that calculation is going on your server, it's going to also overflow onto other people who are trying to be active and use that same server as well. So what we need to do is try and find out what are the most efficient ways to perform the distinct count to minimize the impact. So the next slide I thought I would show. So what are some of the common patterns in DAX to perform distinct count? Now, the number one go-to starting point that I would always recommend is to definitely use the distinct count calculation. In most cases, on most models, particularly if your model is very clean, lots of simple star schema, one-to-many relationships, not using particularly complicated logic in your DAX, this would be your starting point. But as always, when you're doing performance testing, just benchmark, test, log, and you're definitely going to be using DAX Studio for this work. Because that provides so many fantastic features that allow you to understand exactly what's going on. And I have a short demo soon where we will use DAX Studio to try a couple of different DAX patterns against a small data set that I have loaded on my machine. The other one that is quite interesting, and it's you wouldn't necessarily think of it unless you'd seen the pattern before, is using one of the iterators called SumX. Now, SumX, well, iterators in DAX, what they do is they perform a grouping for you. And what this SumX pattern will do is it'll say the column that, whoops, I need to go back, sorry. There. So the first parameter that's passed to the SumX function is a list of values. And in this case, we're providing a distinct list of values. And if the distinct values in whatever table and column happen to be 17 distinct values, then the SumX will iterate in a loop 17 times. And all we're doing is we're summing up the value of 1, like a count. So the hard work is actually done here, but we're grouping. Now, the difference between these two is where the grouping and the counting takes place. And the short answer, but I'll show this in my demo, is that DistinctCount will perform the work in the storage engine as much as possible, which is can be very, very fast. Whereas this SumX distinct pattern tends to bring the data from the storage engine into the formula engine and do the work there. But hopefully my demo will explain that nicely, because I'm going to be showing you these two patterns. I see this sometimes, count rows distinct table column. Now this should give you the same value as the two previous examples, but quite often what you find is if you look under the covers, this count rows pattern often just simply gets rewritten as distinct count. So if you're doing this and you're thinking you're possibly going to get different performance, then the chances are, if you wrote your calculation using distinct count table column, that you'll probably end up with exactly the same performance characteristics. Lastly, yep.
Sorry to interrupt, Phil. Just
Sure.
one quick thing, because some of our audience might not know what is storage engine or formula engine. Can you just very briefly just explain that a little bit?
Sure, happy to do that. So in DAX, there are two engines. Every time you run a calculation, there are two engines at play. The storage engine, it focuses on going to the underlying database and collecting the data and bringing it back. While the formula engine allows you to perform more complex calculations. And the analogy I'd like to use in other sessions is, if you consider the idea of baking a cake, the calculation is your recipe and the output is the cake that comes out of the oven. Now, the storage engine is your trip to the shop to go and get the ingredients, the data. Now, let's say you need 10 ingredients for this fantastic cake. There's flour, egg, sugar, and some other fantastic things. An orange cake with cream cheese icing, the best. Now, what you can do is you could make 10 separate trips to the same shop to get one ingredient, or you can make one trip to get 10 ingredients. Now, that activity is the storage engine. And believe it or not, some of the storage engine tasks, they can perform some functions, like they can pre-bake the cake along the way. So you could have a storage engine task which is optimized to do summing, and another storage engine task which is optimized to do a max or an average, or even distinct count. There is one there. So ideally, what you should try and do is push your task of baking the cake, which is to complete your calculation, to the trip to the store. So when it comes back, it's done, it's ready to go, and the formula engine has nothing to do. Or you can push all your work to the storage engine that just simply goes and gets the data, gets the ingredients. And this can happen in parallel. You could have 10 people that in parallel go to the storage engine to really, really, really speed things up. It doesn't make sense in my cake analogy, but it does in the data analogy. And then once you've got the ingredients back, and they're still wrapped up, they're still in their packages, the formula engine waits until the last person is back from the store, and then starts the work by performing the calculation. So with DistinctCount, most of the work happens in the storage engine, so can be very good, depending on the selectivity and the cardinality of the data. Whereas the SumX approach pretty much just goes and gets all the ingredients and then gets them back and then does the work. And they both have pros and cons. Typically, the rule of thumb is you try and optimize your calculation to get the storage engine to do as much of the heavy lifting as possible, leaving the formula engine to just, which is only single threaded, there's only one chef, to do as little work as possible, which suits me. So hopefully that answers your question, but I will have The example that I'm going to show in my demo, I'll be looking at the formula engine and storage engine profile when I run the calculations.
Great.
So lastly, approximate distinct count. Now, some clever mathematicians have come up with some smart mathematical shortcuts that can arrive at a value very cheaply and easily. That's not giving you the exact number, but it's giving you a number that's so close it's well worth considering, particularly over very large data sets. And these calculations are much faster than the exercise I showed you earlier, where you have to precisely go through every single value in the data. And there are a couple of ways that you can do approximate distinct count in Power BI, and we'll touch on those as well. So they wouldn't suit a financial application, but when you do a search on your favorite search on your favorite search engine, such as look for help on DAX, it's going to come back with it's going to show you the top 10 results, but somewhere near the bottom it's going to say, hey, I found 55,000 results. Now, it didn't actually find 55,000 results exactly. It probably found 55,124, but you get the picture. Didn't find 100,000, didn't find 200,000. It found a number very, very close to 55,000, and that's good enough for me, because I might be interested to know, how popular it is just simply by looking at the number at the bottom. But it can produce that number very fast, whereas if it was to actually go and look at every single web page and take the time to catalog them and group them and check to see whether they were new or not, it would take a long time. So there is a use case for approximate distinct count, and I'm just going to touch on different ways that you can use that in your Power BI model. So I do have a couple of demos here. So I'm going to jump to my Power BI report, and I have a very simple report here. I have one fact table at the bottom called fact sales, and this is a nice star schema. So we have 3 dimensions, the classic date, store, and product. So this would probably resemble quite closely a lot of models that I see. And okay, now what I'm going to do is fire up the very good DAX Studio, using the external tools, which I really love, and I'm really enjoying seeing all the fantastic tools that are popping up in there. Power BI top tips have even got a launcher that you can download and install to help you plug in these great tools. And actually, if we go back to my Power BI report, I want to see in my fact table how many rows have I got. So my fact sales table has 3.4 million rows, so that's quite important to note. And my date table has got 2,556 rows. So the fact table has 3.4 million, and my date table has about 2,500. So where was my DAX Studio? So the first pattern we're going to have a look at is the distinct count pattern. And what I'm going to do is run this top calculation here, which is I want to perform a distinct count over this column in my fact sales table. This is my 3.4 million row table, but I'm going to group it by my store types. Now, let's have a look at the characteristics of this data model. So in DAX Studio, what I can do is look at the metrics of my model. And down here in the bottom, what I can see is my fact sales table has 3.4 million rows. And when I expand fact sales, I can see that my sales key column also has exactly the same number of rows. So I've deliberately engineered this calculation so that we can look to see how it performs. This is going to produce some very high numbers, but it's going to be grouped. How many groups have we got here? We can have a look at the dim store table. There are no other filters going on with this calculation. And the store type column has got just simply 4 values in it. So we're going to return 4 rows, and we're going to calculate this. It's going to return a high number, but let's see how that performs. So I'm going to turn on my server timings, which is going to show me how much time was spent when I run this calculation in the formula engine versus the storage engine. Plus, it's going to tell me how long it took to run it overall. So we're going to clear cache and run this, and that's completed. We have some results, pretty quick, 4 rows, as I said, and there's some pretty high numbers in here. So there were 2.1 million people who came into the store, or 2.1 million transactions effectively. And the server timings show that it was able to perform a single scan that took 1.5 server seconds, because it could parallelize this. It only took 600 milliseconds to complete, but it did very little in the formula engine. All the work was done in the storage engine, which is pretty cool. So now what I'm going to do is open a SumX version of the same calculation. So I'll put these side by side when this opens up. Excellent. We can park that, make this smaller. There we go. So this top calculation here, I have over here using the other pattern. We're grouping by the same store type in line 3, and then in line 4, we're using the SumX distinct approach over exactly the same column. And if we turn server timings on here, have I got this on? I can't remember, sorry. Server timings. Oh, so I need to click on here. There we go. Waiting for trace to start. Highlight the query and run. Nice. Okay. So the first thing we can see is it took 2.3 seconds. And of that time, now remember this is server elapsed time, so it did split this up. There was only one scan. It spent nearly 3 seconds going and getting the data. And over here in rows, we can see that it actually got all 3.4 million rows from the data set. It needed to collect all that data, and it brought it back to the formula engine, and it did the rest of the work in the formula engine. So here was where the SumX kicked in and did the grouping and then did the calculation. So the storage engine, there was no value. And if I showed you the query plans, for example, you'll see that the storage engine task just did a simple go and grab and collect, whereas over here the underlying query plans actually performed a distinct count during the storage engine work. But we can see that in the numbers and how much or how little actually took place. So the next thing I'm going to do is run a different calculation using DistinctCount, and I'm going to kick this off now because this is going to take some time, and I'll explain what's going on in this calculation while this is running in the background. So this time, rather than group by just 4 values, we're grouping by every single date in the date table, and that was about 2,500 dates. That's an important number to remember. And what we're doing is we're performing a distinct count of the sales amount column, but we're putting in a complex filter. We're saying, don't just do it for my date, do a distinct count for whatever day you happen to be sitting on, plus all the values from the previous day, plus all the values from the previous day. So it's probably not a calculation you're going to see necessarily a lot in BI, but it helps show the difference between what's going on in these two patterns. So it's completed. That took 45 seconds to complete. And down here in the bottom corner, we can see the number of storage engine queries is going nuts. This is not a healthy calculation by any stretch of the imagination. And this is going to count up to 2,500, which happens to be one storage engine query for every single day in the date table. Not very efficient. So it still did a lot of work in the storage engine. This is a huge amount of work that's been parallelized out. And you can see that there's lots and lots and lots and lots of, well, 2,500. It's basically for every single day, it's performed a subquery and gone out and had to do the work, a lot of work. Over here on the other side, we have exactly the same query. The only difference is line 14, instead of having distinct count over the sales amount column in the fact sales table, we're using SumX distinct over the fact sales table, the sum amount column. And if I put the results here, now if we run this, now remember previously we spent about just under 3 seconds in the storage engine collecting all the rows from the fact table, and then we tidied it up in the formula engine. Let's run this now. And boom, so it's complete. So it actually spent less time in the storage engine and didn't collect as many rows. It was smart enough. It could do a couple of queries on the date table first to work out what days were necessarily relevant. And then it decided, okay, I need to get about 1.8 million rows from the storage engine. I'm going to bring that into the formula engine, and then I'm going to do the SumX work here. So let's just quickly look at the results just so you can eyeball that the results are exactly the same. So in the server timings here, our total elapsed time was 4 seconds, 4.3 seconds over here, 46 seconds. So it was 10 times faster. And but as you can see, it wasn't using the storage engine to its full capacity. It was just getting the data and bringing it to the formula engine. And here's where it did the iteration and to arrive at the numbers. And the reason why is because in this case, because we were also asking the calculation to do this tricky, what I would describe as a slightly complicated extra task. Over here, DistinctCount decided I can't do this, so I'm going to have to, I can't do this in the formula engine. I'm going to still try and do this in the storage engine, but I'm going to make lots of trips to the store, one for each ingredient. Whereas over here, the engine decided, okay, I'm just going to go bring the data into this formula engine and perform this calculation over there, which is pretty cool. I'm going to just try and find my memory profile, because I think another interesting characteristic of this is what memory looks like when I'm running this slower calculation. So, okay, so I'm going to clear cache I'm going to click back on my SumX, clear cache, and whoops, I need to go back to my DAX Studio. And cool, okay. It's just going to stay in front of us. Hopefully it does. All right, well, let's just clear cache and kick this off and go back to my view here. Now, what I'm looking at here, I've just kicked off this query. You can see my memory jumping up and going crazy, and also my CPU going crazy with this technique. So remember, this is going to run for 45 seconds, and this is my personal machine going nuts, and this is going to take another 20 seconds to complete. Now imagine this is on a server, and imagine you're doing this over a very large amount of memory. Now this model started at 500 megabytes in memory, and just clicking the run button on the query, you can see it's already up to 940. So it's an extra 400 megs of memory that it's needed to set aside. Remember the card exercise that we walked through earlier to do this? It's nearly complete. So this is I/O. My CPU is busy, and my memory is busy. So it's completed the calculation now, and it's just busy writing this out. And what I'll do is I'll run this calculation, which only takes 4 seconds, and we'll have a look at the difference in the profile there. We'll just let this complete. Has to count up to 2,500, and nearly there. Cool. And if I click the clear cache button, what you'll see is my memory will drop back down to baseline. I'll just park this out the way so I can find it again. Click over here, highlight this calculation, run it again, bring back my memory and CPU, and you can see the profile does increase memory. No, by nowhere near as much, but look at that. It stopped. My CPU here barely registered, and now we're back to normal. So if I clear my cache, there we go. So we're back to normal. So that's a sort of a demonstration on how different approaches can have quite different results depending on the grouping, the underlying data, the selection or selectivity, etc. So just remember that it's always good particularly when you've got the slowest page or the slowest visual on your report, just try some different techniques and approaches and use tools like DAX Studio, etc. to see what's going on, and you might find you'll come across a better way. So what are some other options when it comes to distinct count?
A question,
Sure.
Phil, sorry, from Vishesh. What if this runs on the service? Will it impact other users?
Absolutely. Yep, absolutely. So the service is just still a machine at the end of the day. And if you have a very inefficient distinct calculation that's running over a huge number of calculations, let's imagine that you've got something that runs for 5 minutes and chews up a lot of memory, then yeah, everyone else on that box is going to potentially get queued up. So that's why it's especially important with distinct count calculations to really make sure that you're using your memory and your CPU efficiently. Like I said, the storage engine can run in parallel. I have seen machines with 40 CPUs get completely bogged down, lock out people simply because of a distinct calculation. Chews up all the storage engine threads for 5 seconds, for example, and that's it. Everyone else is just queued up behind. So absolutely, it can impact other users. So
thank you.
So that's why I'm showing you these different ideas and techniques. So hopefully that answers your question.
Yep, thanks.
So other approaches that you can take, you can pre-calculate like in aggregate tables, but you have to be very careful here because, well, if you try and create a table with exactly one row per what your distinct count would come up with. So if you think back to the idea of the users coming into the shop that I used earlier. So on Monday, instead of having a table with 3 transactions, because I had 3 people come in, bin came in twice. I would have a table with just 2 rows for Monday. And then on the Tuesday, I would have as many rows as there were unique people that came in. So that means I don't need to use distinct count or SumX. I can just count rows, and that's going to be a lot more efficient. However, the pre-calculated table needs to be precisely matching the grain of your query. So if someone then drags in a column to say, I just want to look at people who are left-handed or right-handed or some other way to split things up, you can't use that pre-calculated table. You need to then jump to another pre-calculated table which now has exactly 1 row per grain for that dimension selection. So what you gain in terms of performance and memory usage, it'll cost you in terms of managing and maintaining the number of aggregate tables. I've seen models successfully built with perhaps 20 tables like this for the really important criteria that people most commonly select. It does take a lot of work, but if performance is your number one priority, then it's an option. It's not. I wouldn't say it's your go-to option first up, but you can do it. It can be done. And yeah, like I said, my 4th point here, it can meet a lot of tables. Approximate distinct count we mentioned earlier. So there's a couple of ways you can do this. So there is an approximate distinct count function inside DAX. However, what's really important to know is that it only works with direct query. The DAX engine itself has no native concept of approximate distinct count. All it does is it pushes it out to a data source that supports it. And I believe that still only is Azure SQL DB and Azure SQL DW, or what you might call as Synapse. So if you spin up a box, Azure SQL DB or Azure SQL DW, and just write some T-SQL, there is a function there called approximate distinct count. So if you have a very large table and you want to get a distinct count over a column, it might take 5 minutes to arrive at the result. Or you could rewrite your T-SQL to say, give me an approximate distinct count, and it might take only 20 seconds and give you a number that's not exactly the same as what you previously got, but it's very, very close. It's within plus or minus 2%. So in DAX, you can only use the approximated distinct count function with a data source that supports it. SQL Server, say on-premise 2019 might do. I don't know. I haven't done that pre-research, but if you are sitting on that, I'm pretty sure you could figure that out fairly quickly if you want to try that out. The other approach, if you're really, really keen, is to roll your own. So you could go to the internet and do what I did and do an internet search for what we call HLL, or Hyperlog Log Plus. Now, this is a popular algorithm used by organizations like Google and Facebook, who have incredibly large calculations to perform when they're trying to understand trending of users, who are hitting their system. They don't want to do a distinct count. Getting within plus or minus 2% is much more efficient. So a bunch of very smart people came up with these mathematical shortcuts and published them, and said, if you apply this, if you apply this formula to your data, then you should be able to arrive at these numbers. So I had a crack at this last year, and I do have a DAX. I do have a blog on my website, which I'll share a link to, with a lot more detail. I'm not going to go into that detail here. I'm just going to show you the what the results I found when I applied it. I grabbed a data set here at Microsoft that had 50 billion rows. It was some telemetry of one of our tools. It was anonymized, but it was real life, a demo, and it was activity over a couple of years. So I was interested in doing things like, say, for a given year, how many distinct users have a record somewhere in this data set? And this was 50 billion rows. It was like quite a significant amount of data. And what I did was I first of all imported all that data into an analysis services database, just a big version of Power BI, and I performed, so it was all in memory, and I performed a distinct count calculation, not using this HLL approximate. I actually performed a distinct count and measured how long that took for a variety of queries. And then I applied this technique where you could use these the algorithm, and it's not particularly complicated. It can't be, because I managed to get it going. So as I said, it's based on HLL plus, which is hyperlog log. It's really fascinating reading if you like this kind of stuff. It uses very little memory. This is a big important thing, particularly on a server that's running these calculations often and over a big data set. It can be much faster, and as I mentioned, the accuracy, certainly I found, was often way more accurate than plus or minus 2%. It was rare to see the accuracy blow out to more than 2%. So let's have a look at what the results were. So I had 5 different types of queries, similar to what I showed you in the DAX Studio. Some of these queries had a high cardinality, others had lower cardinality. So query 1, which was the one that gave me the most impressive results, this was just simply group my 50 billion rows by over 3 years and give me the distinct number of users. So when I ran that calculation using DistinctCount, it took 173 seconds, and the memory profile was pretty impressive, as you can imagine. The equivalent in HLL using approximate DistinctCount was only 6 seconds, so it was 25 times faster. And then some other queries were 13 times faster, 7 times faster, and some smaller ones were only twice as faster. But the accuracy, when you average the accuracy, it was less than 0.25% difference. So let's have a look at the accuracy. So this accuracy results is just for query 1. So when I wanted to understand what is the distinct count of users for 2019, it was 143 million. For 2018, it was 138 million. So these are the precise values that took 173 seconds to compute. The value that HLL came up with for 2019 was 143 million. It was only 0.67% out, and you can see that the physical difference was under 1 million, which is pretty big. I wouldn't want to be that far out on a financial calculation. But what we can see for the 2018 and the 2017 versions, the value that DistinctCount came up with compared with HLL was only 52 and 23,000 difference. So it was 0.04% in terms of accuracy, but we're talking 25 times faster. So let's have a look at the memory profile. So I performed this calculation 3 times, and the 173 seconds that the baseline took was an average of these 3 runs here. So they were taking anywhere from 171 seconds to 177 seconds. But when that ran, the storage engine was just a huge amount of work. And you saw the formula engine stuff go crazy when I was doing the distinct count in my previous example. So if I'd kept those charts, actually, they would be quite impressive. You would see memory go skyrocketing up for the period that the query was running, and a little bit of effort in the formula engine. But HLL doesn't do distinct count. It can effectively arrive at the value just using sums and divisions, and that's pretty much it. So there's a lot less work happening in the storage engine because sum is much more efficient than distinct count. Nothing happening in the formula engine. So that's pretty much why it could produce the number on average of these three figures. So I've got a lot more detail in my blog. I can share I have a link in my references page at the end of this. It's a long read. And it's actually a technique that doesn't necessarily it's unique to DAX. You could apply the technique to any database engine. You could apply your own HLL and SQL or Access or any database flavor that you like. All you need to do is pre-calculate a couple of columns that are going to have a small number in it, and then the calculation just runs on those. And in fact, you could actually remove the user ID column out of your model if you're comfortable with this accuracy, and reduce your size of your model if you really want to go crazy. So how are we going for time here? Let's just let's wrap up here, and then we can go to questions.
Great. You have just one question, which is kind of related to distinct count. Fernando is asking, like count rows values, is it acting similar to count rows distinct?
No, it's probably going to. Yeah, okay, so count rows values and count rows distinct will practically be the same. The only difference between the distinct function and values function is how it handles blank values, or gaps where you've got items in your fact table that you don't have a row in your dimension, or the other way around. I can't remember off the top of my head, but one of those two will give you a slightly different result unless you've got perfect referential integrity. Otherwise, they probably will. I expect they probably will perform practically the same. And are probably rewritten internally to behave like if you were to use the distinct count function in the first place. Right. Yeah. So
great, thank you.
So I think the two main patterns that will give you the quite different approaches are probably more the distinct count function versus the SumX approach. So I would bounce between those two depending on what the data set was. But like I would always start with distinct count.
Yeah, and I suggest everyone to, like, if you ever have a doubt, like which one is better, which one is worse, you can always go and give it a try in DAX Studio. Look at the metrics that Phil just showed in his demo. That would be a great way to realize that how much they are different.
Yeah, absolutely. DAX Studio is a really, really good tool when it comes to optimizing for performance. It's essential. And there's some fantastic videos and blogs and examples on how you can use that. Marco does a ton of it. Anything by Marco obviously is going to be well worth watching. Absolutely. We had a look at some DAX patterns. As I mentioned, always start with distinct count and then test and benchmark. Absolutely. And come back and check periodically too, because new data coming into your underlying data set might change the profile. That mean that while distinct count started as the more optimal approach, that over time what it might mean is the SumX could be worth considering if it does turn out to be one of your slower performing visuals or calculations in your model. Yeah, and we touched on approximate distinct count. So hopefully I've just given you a flavor about what it is, what it does, the strengths and weaknesses of it, when you might use it, and how you might use it. It definitely has a place, but you would always probably start with distinct count initially, but hopefully you can get an idea of why distinct count can be the resource hog in the engine. So some references, and I'll save this PowerPoint deck somewhere on the YouTube link, or somewhere that Reza tells me to park it afterwards, so you can click on these if you don't want to type these out. So again, SQL BI, Marco and Alberto have got some fantastic articles on the strengths and weaknesses, and they explain in a lot more detail as well about what's going on when you use those two approaches. So definitely well worth reading. The middle link is the link to my HLL roll your own version of approximate distinct count. And if you do that one, I'd love to hear from you, particularly if you manage to successfully implement it. I know I've talked to several people, quite a few people who have used that, and they report that it's worked really well for them. And finally, don't forget that we last month put up a new free DAX training learning path on Microsoft Learn. I highly recommend adding this to your multifaceted approach to learning DAX. Combine this with the books and the training that you're also doing. It's not designed to make you an expert in DAX, but it should get you a long way, well along the way. So I highly recommend have a look at that among all the other training that you're doing. So that's all I have time for today, Reza. So perhaps we can go back to questions if you like.
That's fantastic. Wonderful presentation. So we got a couple of more questions to go through. One is from Donald asking, could this be applied to distinct? Let me switch to this view as well. So question is that could this be applied to distinct transaction in a table where you've split a large transaction ID into more than one column, like date, store, trans number, where the table is at the line level? Not exactly sure what that question means.
No, I'm not clear either. So I wonder if you mean that your transaction number is very large, like in the billions, and you split it up into 3 columns, like the value from the thousands and the millions and the above millions into 3 columns. This is often a technique that people apply to get better compression, to reduce the size of the model, but the cost is at execute time. You need to sew them all back together. If that's what you're doing, once you've sewed them back together, then absolutely you can use these techniques to do a distinct over. But I'm not sure if that's the case of the question. I might have got that wrong. Sorry.
I think maybe, like, this is what I'm thinking. Maybe his question is related to like scenarios that you have like the transaction ID combination of like the date, the store, and things like that. And if you split it into separate columns, they would be like much smaller, distinct values rather than like the cardinality, reducing that. I think that is the question. Yep, trying to reduce size.
Yeah, so you could either perform distinct over those separate columns, or you could you sew them back together. But if you're sewing them back together at runtime, there's going to be that cost, that extra piece of work that needs to happen. And when you're doing distinct count, you're already forcing the engine to do a lot of work. So whether you want to like add on this extra overhead onto the top, I'd probably want to look at that in a little more detail before I tried to give any strong, hard, fast recommendations. So I'd hate to steer you wrong, but it sounds to me like you're making the distinct count calculation do extra work at runtime, which doesn't sound right.
Yeah, that might be a good approach for the model size, to reduce the model size, but it might not be a good approach for the distinct count. Great. One last question that we can wrap up. It's not much related to distinct count. It's a question from Fami asking, how would count X and count AX perform compared to sum X?
I don't actually use those functions a lot myself, count X and count AX. I seem to see them often from people who have come across to DAX from Excel. And I think people make the mistake that they perform exactly the same function in DAX that they do in Excel. So without looking at this too deeply, I suspect functions like SumX with the 1 may outperform count A and count AX, but I don't use those functions enough in the work that I encounter, which possibly means they, for performance, aren't necessarily go-to ways to solve your calculations. Because what are they doing? Count A and count AX, they count the unique numbers in a series or something, and they have to be numbers. Off the top of my head, I can't remember. Do you want to reach out to me and maybe give me an example? I think my details are in the YouTube bits and pieces, and send me a little dummy example with a handful of fake values, and then I can take the time to give you a proper assessment and consultation for free.
Fantastic. Thank you. And just I add one thing to this, like count X, count AX. At the end of the day, sum X, average X, all of these at the end of the day are iterators. So iterators, they all have like same behavior of going through like every row doing the calculation. But feel free to use fields free consultation on this if you have any questions. And thank you everyone for joining. It was a pleasure to have you here. Phil, any last words?
No, just thanks for inviting me, Reza. And yeah, hope everyone stays safe. And yeah, thanks for taking the time to jump on and listen to DistinctCount. Hopefully you learned something today.
Pleasure. Thank you. And thank you everyone for watching again. It was great to have you all here. See you next time.
Okay.
Stay safe.
See you later. Bye-bye.
Okay, that went.
So we're off.